dear students. In this session, we are going to discuss about optical instruments. So these optical instruments are designed by using certain properties of light, that is reflection, refraction of lenses, mirrors, prisms, etc. So examples for this optical instruments is like our simple microscope, telescope, binoculars, periscope, etc. Okay, in this we first discuss about microscope. Later we discuss about that telescope. Okay. So what is microscope? Microscope is an optical instrument. What is microscope? Microscope is an optical instrument. It is used to see the small objects, very small objects which cannot seen by naked eye. Okay, what is microscope? Microscope is an optical instrument used to see very small objects which cannot be seen by naked eye. So there are two types of microscope. They are simple microscope and compound microscope. Okay, simple microscope and compound microscope. So first one is simple microscope. So the simple microscope is just a converging lens or convex lens. Example for this simple microscope is our reading lens. So reading lens is the example for the simple microscope, that is also called as magnifying lens. Okay. So this simple microscope is just a convex lens like this. So this is the convex lens. Draw a principal axis. So this is the optical center. What is simple microscope? Simple microscope is just a converging lens of small focal length. Okay. So this is principal axis. So this is the focus, that is F. Focus. Sorry, this is focus F. Now, where we have to place this object? So we place the object near to the lens. We place the object near to the lens, or we place the object between the optical center and principal focus like this. This is the object, that we call this object as A, B. We place the object between this. Once again, we place the object between this principal focus and optical center. Let us consider a ray of light entering to this lens, convex lens. What happens? It gets refracted. It gets refracted like this. After refraction, it focuses on the principal axis, that is the principal focus. This is the incident ray and this is the refracted ray. After refraction, they make at the principal focus on the principal axis. Okay, let us consider one more ray which is incident along the optical center. Consider one more ray. This is the object AB. Consider one more ray from the object which is incident along the optical center, which moves undeviated. When a ray passing through the optical center, which moves undeviated. So this is the another ray. The one ray incident on the lens which is passed through the principal focus, and another ray which is incident on the optical center and they pass undeviated. So when the observer sees this rays from this point, it appears as diverge from a point. There appears to diverge from a point like this. There appears to diverge from this point like this. So this is the image of an object AB. This line is the image of an object AB. So this is A dash and this is B dash. If we extrapolate this in the backward direction, so we get image of an object. So this image formed by this lens is virtual, erect and enlarged image. Image formed by the Simple microscope is virtual, erect and enlarged image. Okay. So for this we have to write a formula for the magnification. So magnification is, we know that magnification is the ratio of height of image to the height of object, or it is also defined as the ratio of image distance to the object distance. Okay. But we know the formula, lens formula, that is 1 by f is equal to 1 by v minus 1 by u, where f is the focal length, v is the image distance and u is the object distance. Now rearrange this equation to the 1 by u. So 1 by u is equal to 1 by v. 1 by u is equal to 1 by v minus 1 by f. Now substitute the value of 1 by u in this equation. You will get m is equal to v into 1 by u. 1 by u means 1 by v minus 1 by f. So we get cancel. Remaining is m is equal to 1 minus v by f. Here v is the image distance and f is the focal length. Here the image of an object AB is formed at a distinct vision. Image of an object AB is formed at a distinct vision. So distinct vision means it is the minimum distance in which the object can be seen clearly. So here v is equal to f. V is equal to f. By applying sign convention, you will get v is equal to minus f, because here this is the distance, image distance, that is d, which is measured opposite to the direction of incident. This is the direction of incident ray, but we measure this distinct vision d in opposite direction. So v is equal to minus f. V is equal to minus d. So m is equal to 1 minus of v means minus d, that divided by f. So m is equal to 1 minus into minus plus d by f. So m is equal to 1 plus d by f. So this is the image formed at near point. Image formed at near point in the microscope. Okay. In your board exam, you need not worry about this expression. No, you need not worry about the derivation of magnification. You just remember the formula for the magnification, that is m is equal to 1 plus d by f. Okay. Ray diagram, you remember this ray diagram and magnification power formula. Okay, this ray diagram carries 2 marks and magnification formula carries 1 mark. Okay, here d is the least distinct vision and f is the focal length. In this case, we have to derive the formula or expression for magnifying power of a simple microscope when the image is formed at infinite distance. In the previous case, we have to derive the formula for magnification power of a simple microscope when the image is formed at near point. But in this case, we have to derive the formula for magnification power when image is formed at infinite distance. Image is formed at infinite distance. Okay. For this, let us consider a convex lens like this. Once again, let us consider a convex lens like this. So this is the convex lens. So this is the principal axis. Let's draw the center line. This is the optical center. In the previous case, we kept object between the principal focus and optical center. But in this case, we kept the object at the principal focus. We kept the object at the principal focus, that is F. Okay. When, this is the object A, B, when a ray of light entering to the lens like this is the incident ray, it gets refracted. So after refraction, it is focused on the point of the principal axis that you called as principal focus, that is F. After refraction, it focuses on the point of principal axis, that is called as F. So this is the refracted ray. Let us consider one more ray which is passing through the optical center of the lens. The ray which is passing through the optical center of the lens moves undeviated. Consider one more ray which passes through optical center, which moves undeviated. So these two are the refracted rays. For an observer, see these rays from this position. What will see? If we extrapolate these rays in the backward direction, so if we extrapolate these rays in the backward direction, these rays cannot meet. These rays cannot meet at a finite distance. That's why image is formed at infinite distance, because these two refracted rays, after refraction, the rays are moves parallel. The parallel rays cannot converge at finite distance. So image is formed at infinite distance. So in this situation, image is formed at infinite distance. Okay. To determine the magnification formula for this case, we won't discuss about the linear magnification. We discuss about angular magnification. Because here the image is not formed at finite distance. The image is formed at infinite distance. So for infinite distance, we cannot define linear magnification. We define the magnification in terms of angle. Okay. So this angular magnification is defined as ratio of angle formed by the image at I to the angle formed by the object at I. It is the ratio of angle formed by the image at I to the angle formed by the object at I. That is, angular magnification M is equal to beta by alpha, where alpha is the angle formed by object at I. Beta is the angle formed by image at I. Okay. To derive the expression for this angular magnification, we measure this beta and alpha. So to denote this alpha, let us consider an object. Simply, an object is kept inside the in front of the eye. So the rays coming from this object is entering into the eye and converges at a point like this. Okay. Suppose this is the angle sustained by the object. This is not required. This diagram is not required. For better understand this, you know it. Okay. This is the angle. Sorry. Shall I write again? So this is the object. When rays coming from this object is incident on the our eye, so it is focused on the point. So this is the angle made by the object. Okay. So this is the height of object, that is HI, and this one is the object distance, that is D. Here the object is placed at least distinct vision. Object distance is U, but the object is placed at least distinct vision, that is D. Okay, least distinct vision is the object can be seen clearly for our naked eye, that is for human being this least distinct vision is about 25 centimeter. Okay, so we define tan alpha here. What is tan alpha? Tan theta is opposite by adjacent. Here tan alpha is opposite by adjacent. Opposite is height of not image object. So height of object to the D. Tan alpha is equal to h naught by h. Here alpha is very small, angle is very small. So for small angle, tan alpha is approximately equal to alpha. So this becomes alpha is equal to h naught by d. We call this as equation number 1. Now we consider the second case, that is the angle sustained by the image at I, that is beta. So here the parallel rays cannot meet at the finite distance. This parallel rays cannot meet at a finite distance. Suppose if I consider this parallel rays are meet at some finite distance and forms an image of this object at a certain height like this. Actually, the image is not formed at this distance, but derivation purpose I will show. But the image is formed at infinite distance. So this is the image distance. This is the image distance. Okay. So this is the angle sustained by the. So this one is the angle sustained by the image. So that is beta. These are the alternating angles. So this is beta. This is beta. This is also beta. Okay. So here from this is the image. So this image is HI. Okay. So this distance is nothing but what is that? Image distance, that is V. Okay. Here tan beta is equal to HI by V. Tan beta from the triangle, tan beta is equal to height of image to the image distance, that is V. Okay. So this is not actually necessary, but for derivation purpose I will show you. Sorry, I have shown you. Okay. So HI by V. If theta is very small, this expression becomes beta is equal to HI by V. But we put a negative sign for V because this image distance is measured opposite to the direction of incident ray. So we will get minus V. So for small value of beta, this tan beta is equal to beta. That is beta is equal to HI minus V. Okay, HI minus V. HI is the image distance and V is the object. Sorry, HI is the height of image and V is the image distance. Okay, but we know that magnification is equal to height of image to the height of object. That will be equal to image distance by object distance, that is HI by HO is equal to V by U. Therefore, HI is equal to what? HI is equal to V by U into H naught. So, I will substitute this in equation beta, that is beta is equal to HI is V by U into H naught into minus 1 by V. Here V get cancelled. Remaining is beta is equal to minus HO by U. Minus HO by U. Okay. But here U is the object distance. Here U is the object distance. The object is placed at the principal focus. So this object distance is itself focal length. But we consider this object distance as minus F because we measure this object distance opposite to the direction of incident ray. Therefore, we put U is equal to minus F. So this equation becomes beta is equal to minus H naught by minus F, that is H naught by F. Okay. Now substitute this alpha and beta in the angular magnification. Shall I write here? Magnification M is equal to, what is that? Beta by alpha. Here beta is H naught by F by alpha. By alpha is H naught by D. Sorry, that is D by H naught. H naught can cancel. Remaining is M is equal to D by F. So this is the expression for magnification power when the image is formed at infinite distance. Okay. So in this case, we worry about only ray diagram and this final expression. You need not worry about this derivation. Okay. You remember only the ray diagram and formula for the magnification of image formed at infinite distance in the microscope. Shall I write here? What is the expression, final expression for the magnification power when the image is formed at infinite distance in the microscope? That is M is equal to D by F. M is equal to D by F. In the previous case, when the image is formed at near point, we get the formula for magnification as M is equal to 1 plus D by F. For this case, when the image is formed at infinite distance, we get the magnification formula as M is equal to D by F. The ray diagram carries 2 marks and this formula carries 1 mark. It is clear? Now we discuss about compound microscope. The simple microscope consists of only one lens, but this compound microscope consists of two convex lenses. One is called objective lens, another one is called objective, and another one is called eyepiece. It consists of two convex lenses. One is called objective and another one is called as eyepiece. Here, the objective lens has small focal length and small aperture, and eyepiece has large focal length and large aperture. Okay. Let draw a ray diagram for this compound microscope. First we draw objective lens, that is a convex lens of smaller aperture and small focal length. Let's draw a principal axis here. Okay. So this is the optical center. So this is the principal focus. Let us kept an object here. Okay. So when a ray of light incident on this objective lens like this is the incident ray and this one is the objective. Objective lens is, that is the lens which is placed in front of the object. Okay. Or the object is placed in front of the objective lens. Okay. This incident ray gets refracted like this. After refraction, it is focused at a point on the principal axis that you called as principal focus. Let us consider one more ray, which is, this is the direction of refracted ray. Let us consider one more ray which passed through the optical center. This is consider one more ray which passed through the optical center like this. This is the incident ray and this is the refracted ray. After refraction, these two rays are meet at a point here. Okay. So this forms the image of an object. That is the image. Here the object is AB. So this is the image of an object AB. That is A dash. This is B dash. Okay. So this is the object distance, that is U. Okay. This is the focal length of the objective, that is FO, focal length of the objective. Okay. So this image itself acts as an object for the second lens. Which is the second lens? That is eyepiece. This image A dash B dash act as an object for the eyepiece. Where we have to draw the second lens, that is eyepiece, we have to draw the eyepiece at a distance of focal length of the eyepiece from this image. We have to draw this convex lens, that is eyepiece, at a distance of focal length of the lens from this image. So this is the focal length of the eyepiece, that is FE. So after refraction, So after refraction, these rays are incident on this objective lens, this incident on this eyepiece, and they get refracted like this. After refraction, they are incident on the eyepiece and they get refracted like this. Okay. For an observer, seeing this rays, they appear to meet from this point. They appear to meet on this point like this. They appear to diverge from this point. So, image of an object AB is formed at this point. This is the image of an object. That is A double dash, B double dash. Sorry, this is A dash, this is B dash, and this is A B double dash, and this one is the A double dash. Where this A dash B dash act as the object for this eyepiece. By adjusting this eyepiece, we will get the clear and enlarged image of an object AB here. That is A dash B dash. Okay. Let I write the expression for magnification power. In this case, magnification power is the product of magnification power of object into magnification power of objective into magnification power of eyepiece, because this compound microscope has two lenses. So, magnification power is the product of magnification power of objective and magnification power of eyepiece. Okay, so we know that this is the F0. F0 is the focal length of objective. Fe is the focal length of eyepiece. This gap is called as tube length. This gap is called as tube length, that is L. So, magnification power of objective, that is M0 is equal to HI by HO, height of image to the height of object, that is equal to L by F0, where L is the tube length and F0 is the focal length of the objective, that is M0 is equal to L by F0. Okay, this next magnification power of eyepiece. Magnification power of eyepiece is equal to ME. That will be equal to, shall I write here? ME is equal to 1 plus D by FE, because this magnification of eyepiece is similar to the image formed at near point in the simple microscope. You remember that in the simple microscope, image formed at the image formed at near point is given by M equal to 1 plus D by Fe. In this point, F is equal to focal length of eyepiece. Therefore, M is equal to 1 plus D by Fe. To substitute this, you will get M is equal to M0 is L by F0 into ME is 1 plus D by Fe. So, M is equal to L by F0 into 1 plus D by Fe. This is the expression for magnification of microscope, compound microscope. That is M is equal to L by F0 into 1 plus D by Fe. Whereas this L is the tube length, F0 is the focal length of objective, D is the image formed at distinct vision, D is the nearer point, F is the focal length of the eyepiece. Okay. Distinct vision, that is the image distance here, D. Okay. F is the focal length of the eyepiece. Next, telescope. Telescope is an optical instrument used to see distinct object. It is used to see distinct object, that is, for example, moon or stars, etc. So this telescope also consists of two lenses. This telescope consists of two lenses. One is objective and another one is eyepiece. But this objective lens has larger aperture and larger focal length. This eyepiece has smaller focal length and smaller aperture. Okay, let us draw a ray diagram for this telescope. First consider, let's draw a convex lens like this. This is the, should I make it? One second. Draw a convex lens here. This is the convex lens. This is the center portion. Let's draw the principal axis. Okay, so this is the optical center of the convex lens. So this convex lens is known as objective. Okay, now the parallel rays coming from the distant object. Here the object is not kept here because we focus on the distant object. So the parallel rays coming from this distant object is incident on this convex lens, that is objective. It gets refracted, and after refraction it focus on the point of principal axis, that is called as principal focus. Okay, so let us consider one more ray which is passed through the which passed through the optical center. Let us consider one more parallel ray which passed through the optical center, which moves undeviated, like this. This parallel ray moves undeviated, and these two refracted rays are meet at a point. So at that point image is formed. So this is the inverted image of the object. Okay. Now we place another convex lens, that is eyepiece. Where we have to place this eyepiece? At a distance of focal length of eyepiece from the object. Okay, so from this image. So this image itself acts as an object for the eyepiece. Now we draw the eyepiece here like this. This is the eyepiece. So the rays coming, this focused ray again starts its journey like this, and after refraction it gets after incident it gets refracted like this. This ray is refracted like this, and these two rays are meet. If we extrapolate this in the backward direction, these rays are meet at infinite distance. So image is formed at infinite distance. That means at infinity. So when the parallel rays are entering into the objective, it gets refracted and focus on the principal axis. After refraction, the refracted rays are meet at a point. At that point, inverted image of an object is formed. This inverted image of an object itself act as a object for eyepiece. This image itself acts as a object for eyepiece. Again, these rays are incident on this eyepiece, gets refracted in this direction, and if I extrapolate this in the backward direction, so image is formed at infinite distance. Okay, at this point we adjust this eyepiece to get the clear and enlarged. So you get the clear and enlarged image of an object at infinite distance. Once again I repeat, when A dash B dash act as the object for this eyepiece, so the eyepiece is adjusted such that this object lies at the focal length of the eyepiece. So we get the enlarged image of an object at infinite distance. Okay. So now I write the formula for magnification power of telescope. So magnification of telescope is given by M is equal to as ratio of angle sustained by the image at eye to the angle sustained by the object, that is M is equal to beta by alpha. So this beta by alpha can also be written as m is equal to FO by FE. FO is the focal length of the objective, that is F0 focal length of the objective, Fe is the focal length of the eyepiece. So m is equal to beta by alpha or m is equal to F0 by Fe. This is the expression for magnification power of telescope. Okay, here also ray diagram and what is that? Magnification power formula is important. Once again you will remember that magnification power of simple microscope, when the image is formed at near distance, is given by m is equal to 1 plus d by f. 1 plus d by f. Magnification power of a microscope, simple microscope, when the image is formed at infinite distance, is given by m is equal to d by f only. Magnification power of a compound microscope is given by m is equal to L by F0 into 1 plus D by Fe. Magnification power of a telescope is given by m is equal to beta by alpha or F0 by Fe. Okay. These are the formula for magnification power of simple microscope, compound microscope and telescope. Telescope with refracting lens is called as telescope with lens is called refracting telescope. Telescope with mirrors is called reflecting telescope. Okay, telescope with lens is called refracting telescope. Telescope with mirror is known as refracting telescope. Reflecting telescope. Next, reflecting telescope. Reflecting telescope. The telescope with lens objective is called refracting telescope. The telescope with mirror objective is called as reflecting telescope. So the formula for magnification power of this reflecting telescope is given by m is equal to F0 by Fe, that will be equal to R by 2 Fe, where R is the radius of curvature of mirror, and Fe is the focal length of eyepiece. Okay, so this completes the theory part of this ray optics. In next session, we solve some numericals. Okay.